Hello, this is Chris Cal. Today is Sunday, July 8th, 2018, and this concludes my fourth week working on the F110 racing car. So these are the things I want to go through today. I'll talk about pure pursuit algorithm, Rviz to show waypoints, got Hector SLAM and AMCL working, can do better on chromatographer and MIT particle filter, the FOC box is installed, and an Hdmi Emulator for Vnc viewing. So in terms of the car, these are some of the changes in hardware. Not too much now. Now it's really been working on the software. But you notice there's no more vest down here, and instead I put on the immersion board's FOC box, which is basically the vest just in a nicer form, and it fits inside underneath this box. So that's really the only change. I got a couple of LiPo batteries as well. This is the old vest here, which is not in use right now. So most of this video will be showing you directly on the computer what improvements have been made. So let me get straight into that. So normally I've been using Terminator now. I've been learning a lot of simple things along the way as well. Terminator's good just because a lot of times in ROS you need at least 2 terminal windows open. One normally running ROS core and then one running something else. But first let me show you Hector SLAM. So I wrote a launch file for Hector SLAM and it's under something called localization. And essentially what this will do is, let's see, Hector SLAM. This will read in a bag file which contains my laser scans and other information, and it will build a map over time. So it's doing simultaneous localization mapping. I did not write this algorithm, I'm only using it right now. But you notice that this car is going around the second floor of Moore building, and it's able to track where it is as well as the locations. So all the surroundings. In the end it generates a map, and the map that gets generated, I then want to be able to take the car and drive it around in real time. And doing that, I can actually then figure out where the car is localized. So Hector SLAM only relies on ROS's on the scan data. It doesn't need anything like transform data, it doesn't need odometry. Doesn't need anything other than that. So it's pretty cool. Notice the robot's now gone near the end and it's generated the map. So now that we have the map, basically I've saved the map into, let me quit this. So if I go into the Finder for the files, I go into my Sims workspace where everything is right now. By the way, I need to clean up all the code later for the F110 UPenn course. But inside of the localization, instead of launch file, you'll see the Hector SLAM. And this took me a really long time to get working, and luckily Abhishek helped me with a lot of this. But essentially what we have here is it's listening to a ROS bag. It has to use the sim time. And then down here, it's doing a static transform because we need to transform from the base link to the laser. I think I talked about this in the previous video where this is a laser and this is the base link, the center of gravity of the car. So you need that small static transform. It's static because you assume that this is a rigid body and doesn't move. And then down here we have Rviz, where it's opening Rviz with a special configuration file, which is something I learned we could do. That way we don't have to always set all the parameters that we want in Rviz. And then to save the map, I normally run this in the terminal, ROS run map server map saver -f, and the name of the file. In this case I called it Moore because that was the Moore second floor. This then saved inside of here, or I dragged it in. I saved a map of Moore and it looks like a YAML file. A YAML file looks something like this. It's also known as a geotiff sometimes. And it'll have things like resolution, the origin, which can be set. In this case, the origin I believe was set somewhere over here. And you can also set other things, which I'm not exactly sure what they do right now. So the next question is, what do you do once you have something like this? And the thing is, you want to run something like AMCL.launch. So AMCL.launch is going to use a different bag file from the one I used to generate the map. Or perhaps I use the same one, but it works with different ones as well. And here the car is driving through space and the map should be loaded. I have to click on this 2D pose estimate to set an initial point. So I just dragged it, and now that I've set an initial point, it'll help localize where the car is in space. So notice how in turns it's not perfect, but because of the laser scan, the matching, the what's it called, the AMCL particles, it's able to try and localize where the robot is at a certain time. And I also tried this live, and it was able to work very well, even when I did it live driving into hallways that the car had not traversed before and had only scanned. So this is super cool. The car is able to go through, and it's able to generally localize where the car is at each moment of time. Now I may play this 2 times because there's a lot of information here that I want you to notice. Notice here, these red lines are the laser scan data. This is the projected location of the car. And then at the same time, it's also using the TF. Now TF data is not directly recorded by the scans, by the bag file, because right now the car itself only has a FOC box. It's not really recording where it is in space. So we use a trick by using the Vnc ODOM module, this Vnc/ODOM. And you'll notice in the scan file that the Vnc.ODOM basically gives us generally, not very precise, but generally good ideas of where the car has traveled. And the Vnc does this, MIT wrote the code in order to just count the number of wheel cycles, the distance traveled, the angle turned, etc. So if I show you the launch file for AMCL, let me walk you through some of the things here. It looks very daunting, but there's really only a couple parts. So the first thing is it's using a ROS bag to play back. So this was actually a new run I did a couple mornings ago. It's not the same one I used to generate the map, which is good, because that way we can show that it works on other things. We have to use the map server in order to launch this more.yaml map file, which is important. And of course, like before, we also needed a transform from the base footprint to laser. In this case, they call it base footprint instead of base length. All these are just copied and pasted from somewhere on GitHub, but they're all parameters for AMCL. What we really care about is that it is using the odometry. As well as this is important too. This is a message to TF node I got from GitHub where it'll take the Vnc.ODOM and transform it to TF. That way, because AMCL listens to TF, not to odometry information. And then I saved my own Rviz, I believe. And so that's how we end up generating this map. And this literally took me a couple days to figure out. I took about a few days off from work during 4th of July and was able to think it through, and now it works. So now that we have this working, now that we're able to localize a robot in a generally fixed world, the next question is, how do we get the robot to follow points, aka waypoints? And this is where things get a little trickier. So I ended up reading this paper on, let me close this by the way, on something called Pure Pursuit. Matt O'Kelly gave me a good idea for that, as well as Professor Monte. Let me show you the paper. So it's from 1992. I may not even have it here. Oh, I do. So Pure Pursuit is really a pretty simple algorithm, but before I get into it, let me just show you this paper. It's just a technical paper. It's actually pretty simple. One of the simple papers I've read, because a lot of them are very confusing. The idea is that if you have a car at some location, so let's say, let me use my nice fountain pen. Let's say you had your car here. And let's say you wanted the car to go to some point in space. The question is, given your car's location, XY, as well as orientation theta, which is defined as in the world coordinates, what direction it is, so this would be theta right here. Given that, what angle do you need to turn the steering wheels using Ackermann steering in order to create an arc of radius that will get you to that point? The only parameter that's in Pure Pursuit is something called a look-ahead distance. So look-ahead distance is essentially some type of radius that you want the car to look ahead in order to figure out which point it should look at next. Because in a world, this is actually around the Levine second floor where we have hallways on all these sides. When the car's starting, sorry, it's backwards. When the car's starting here, we want the car to be able to follow the set of waypoints. It's actually very dense here, but we've plotted it in a way that doesn't look dense. We want the car to follow these waypoints in a way that it'll actually traverse these. And that's not generally an easy task. Therefore, how do we achieve this? Well, the car will start here, and the car will look ahead a certain distance. It'll find the waypoint, we'll call this the goal point, at some distance away. So in this case, I think I set like 0.5 meters. If you set a look ahead distance that's too far, sometimes when the car gets to corners, it may try to cut off corners and hit the wall. If you set it too short though, the car is going to veer back and forth a lot just to follow every single precise thing. When sometimes you may not need it to veer that much because that's wasted time and speed. So essentially what we do here is we end up having the car follow some certain distance in front. It gets a waypoint. In this case, my list of waypoints is literally just a list or an array of x, y, and I think velocity coordinates, or just x, y for now, keep it simple. And given those x, y coordinates, we want the car to just figure out how to get to that coordinate by turning its wheels. And it's listening to that topic and just subscribing to the odometry like many times a second. So it's actually constantly adjusting its turning radius. So the car is able to follow this, and as soon as it makes a step forward, the car moves ahead a little bit. It's going to look ahead to the next point. And by that time, it already started moving this way, and now it's going to try and move this way a bit, and eventually you can imagine that the car follows it. So given that the car can follow waypoints, let me show you a demonstration. This is still a work in progress, but let me show you what I have so far. So I'm going to, I don't know if I need to run ROS core. For the Hector SLAM and AMCL, we actually don't want to run ROS core, because by running ROS core, Hector SLAM and AMCL already create their own masters, so you don't want two different masters because then it causes problems like almost every single time. So we're gonna do ROS launch. I believe I called it Pure Pursuit after the name of the algorithm, and it's called Pure Pursuit .launch. So this launch file is gonna open up, and now what we're going to see is a Rviz and Gazebo open up. Now this is definitely using a lot of GPU on the computer, so it's actually pretty slow. I may want to turn off Gazebo at some point. But the car is trying to follow these waypoints, and it may be hard to see from Gazebo because I wasn't able to figure out how in Gazebo, but it'll look something like this. I purposely added some turns in the beginning so you should see the car going left, right, and then up here going around. Perhaps better way to visualize this is using Rviz, where I've actually plotted out the waypoints, and I probably need a better way of doing this because you can see it's already kind of slow. Oh man, please don't crash. All right, so I've plotted out the waypoints. It's super slow right now, but essentially if you look at it, it's hard to see, but this car is updating and it literally is following these waypoints, which is awesome. See, it's kind of changing colors every once in a while because Rviz is definitely struggling to keep up right now. Perhaps they need to show less waypoints or something else. But here's the car running, and we actually do see it following the path, which is great. Now the downside is all this is really only being shown inside of the simulator, and we want this to work. And first of all, we definitely want it in the real world, but we also want to be accurately using laser scans to localize. Because right now in the simulator, I'm actually just using the VESC/odometry, which normally is not very accurate, but I think in the simulator, somehow MIT coded it such that VESC.odom actually is the actual location. So it's actually very accurate. So if I open up Gazebo, you'll actually see that the car will make this turn. It won't make all the turns because it's following this path that I've provided it that should complete the loop. Now, in order to bring this into the real world, what we have to do is first in the simulator, give me a sec. First in the simulator, we need to see how it's making the turn. And this is at constant speed. So first in the simulator, we needed to use the laser scans to actually try to identify its location. And then once we get that working, then we can bring it into the real world where it'll try and localize and navigate. Now some challenges here. One challenge is that in the simulator, in order to localize, we will need to have generated a map using laser scans of this map. And then once we have that, then we can subscribe to the laser scan topic in order to then try and localize. Now, my intuition before was that it might be very hard to localize just because all these walls are basically perfectly smooth and can look very much the same down the hallways. However, according to Abhishek and Matt O'Kelly, we shouldn't have any problems there because AMCL Or later on, if we use MIT's particle filter, which actually uses the GPU and is about 100 times faster, or at least uses 100 times the number of particles. If we do that in the future, then it seems that it will be faster, and because it also uses the VEST/ODOM, we should be able to incorporate some data from there as well. So this is a general idea of Pure Pursuit working. Once we have this working in the simulator using the laser scan data, the next step is then to take this into the actual world. It'll be using the laser scans just like it did with AMCL to try and localize itself. However, in terms of localization, we need the XY coordinates to be with respect to some map origin, and I'm having little trouble understanding where the origin is going to be and how we're going to set this dynamically every single time where 0, 0 is. But assuming we have 0, 0 set down correctly, then the robot will be able to use its laser to identify where it is, and then the server on the computer will then take in the waypoints, which we will have given it. I'm not sure how we generate the waypoints in the real world, because in the simulator it's easy to generate waypoints since we can just drive around and we can map the places. But in the real world, we may not actually be able to do that, just because in the real world, yeah, maybe, not sure. Maybe we will actually drive the car in the real world and localize and then listen to the bag file at the same time, like we did in the simulator, in order to figure out where it is. So that's something to think about. But that's cool, this is working. Let me just show you a little bit of the code so far. So I actually got the opportunity to implement Pure Pursuit from the ground up, which was pretty cool. The math is actually pretty simple, but it was a little confusing for me. So inside Pure Pursuit, we have this launch file called purepursuit.launch, and you can notice it's very short. All I'm doing here, first of all, I don't even need this tele-op because I'm not using the joystick anymore, so that could be ignored. I really just added 2 Python files. Visualize markers will, in Rviz, just plot all those waypoints, which is given as a CSV file. And the purepursuit.py is like the control file in order to control what steering wheel the car should go, given its location and the list. So you'll see that here's inside the waypoints, I have a waypoints full loop around more. It's about 1,400 waypoints for the whole loop, which is about what Matt O'Kelly has. He does about 1,000 points per loop around like his office. And it's storing 4 things. It's storing the x-axis, y-axis, x-coordinate, y-coordinate. I believe this is the speed and orientation, or the other way around. But essentially we read that into my script. So I wrote this Python script, which needs a lot of work still, because I only got it working near the end of Friday. It's called purepursuit.py. It's about 113 lines so far. But there's really 6 steps. So first you want to determine the current location of the vehicle. So right now we're using VEST/ODOM, but later we're going to actually use AMCL. So we'll subscribe to some topic. Once you've determined the current location of the vehicle, you want to find the path point closest to the vehicle. And in this case, path point, we're doing a reverse traversal of the list of waypoints to find the closest one. Once you have the path point, that is basically the goal point. I don't know why they define them differently. And then we'll want to then calculate the curvature, and the curvature as described in this paper is actually generally pretty simple. The curvature here is going to be this equation right here, 2x over L squared, where x is relative to the car, the x coordinate, and L is the Euclidean distance. Now, it was a big pain. Step 4 was a big pain. I actually don't see it written here, but step 4 is the step where we need to transform the goal point to vehicle coordinates. And to do this, that took a little bit more trigonometry. Let me see if I have a paper, which I do. So it looks something like this, where if you have your car here, I was doing this on the board with Hussam. Essentially, we want to find this gamma here. This gamma we define as relative to the car's coordinates. So notice this dotted line is its y-axis. What angle is the point away? So we know in the world coordinate, which has x and y axes, we know the angle the car is facing, theta, that's actually given by odometry or laser scan. And then in order to find gamma, we need to find this beta. We just call these random Greek letters, and they should all add up to 90. So the question here is, how do we find beta? Well, beta ends up being the tangent beta equals x over y, and this is the difference x over this difference y. Difference x being the difference between x and the car's x and the point's x, and y, difference y being the difference between the car's y and the point y. Once we have that, once we have beta, we're able to just say that gamma equals 90 degrees or pi over 2 radians minus beta minus theta. And that's basically what I've done in this code here, where I say gamma equals pi over 2 minus theta minus beta. Now, what I was really concerned about on Friday, and was literally thinking about this for 2 hours, was that I was worried about all the different cases where the car might not be facing, it starts off facing x-axis in Gazebo, which kind of messes up the math because ideally it's facing y-axis. But the idea is once the car starts going different directions, if it's facing 180 degrees theta, will that mess up any of the math? Do I need to have cases, like 4 different cases? And luckily this math actually ended up working out well. I just made a mistake where I was doing absolute value before, which shouldn't have been there. So this works now. So in terms of that, let me get on to the next thing to show you. So this is generally working. There's still a lot of work to do. Be working on this. But the last thing I want to show you is this tiny thing is called an Hdmi Emulator. Essentially, I figured out a way to boot up the car and turn on a Vnc server, which allows me to actually graphically see the car from my iPad or some other tablet. So let me show you. If I bring up my iPad right here, for instance, so I'm going to open up something called Vnc Viewer. Vnc Viewer is a software, and by the way, I need to make sure it's connected to the Wi-Fi hotspot that the car is emitting. It's called Chris Car, and this is something that I also set up inside the preferences. But basically I join, and once it joins this Wi-Fi, which it looks like it's joining right now, I will then be able to, did it join? Sometimes it has trouble joining when other devices are joined, especially my laptop. So it may not work. Let me see. Nope. I wasn't able to join the Wi-Fi. Give me a sec. Let me go to my laptop and turn it off. I don't know why that happens sometimes, but it's my laptop. Whoops. Alright, so on the laptop, let me turn off my Wi-Fi. I think sometimes it just messes up with it. If I go back here, let me see if it'll fix anything when I try to connect. It may not. Let's see. Basically how I set up the hotspot is I go inside of here and go into network, and then wireless hotspot is on. Not sure why it's not working right now. It could be that my phone's connected to it already as well. But essentially what we would see is when we open up Vnc Viewer, we would basically see the screen right here. So normally, I think it's connected now actually. You see the Wi-Fi on the top left. So go to Vnc Viewer, hotspot, and I think I fixed it just by turning off Wi-Fi, turning it back on. So this is literally the screen right in front of me. And I can control it using my Wi-Fi with my iPad anywhere. So I no longer have to rely on the lab's Wi-Fi router. I could bring it into the real world. It'll boot up with the hotspot using its own antennas. Downstairs I don't have internet, which is okay. By the way, this thing gets kind of loose sometimes. I'm just tightening it a bit. Yeah, so it's able to do that, and then I can just control it remotely. Now, problem is that when this thing's not connected, it resorts back to low resolution. You may not see it right now, maybe because it didn't boot up with low resolution. But normally, if you boot up without something like the HDMI slot, the Jetson will think that nothing's plugged in, which will cause this to only be 640 by 480 resolution, which is pretty much unusable if you want to really see things. So that's what this HDMI emulator is. It's just a $10 fix that tricks the computer into thinking that there's a 4K display plugged in and you can choose your resolution. Of course, there are software ways to do this, but I wanted to just do something simple. So here's a computer now, and it's all good. Just want to show you that as well. So yeah, this is week 4. Summertime is ending soon. I mean, right now is literally July 8th, and school starts basically this will end mid-August, so it's basically like 5 weeks left, maybe 6. So I'll be doing a lot of things with Pure Pursuit. I'll be teaching this course, or TAing the course, not teaching it. I'll be one of the TAs, one of the 2 TAs in this class. It'll be 20 hours a week. But I think it'll be pretty cool, and I've definitely seen a lot of things already over the summer. So yeah, see you.